Так, значит, теперь должен появиться звук. Появился ли звук? Да, звук появился. Хорошо, тогда давайте начнем. Окей. Today we'll talk about elliptic complexes which generalize elliptic operators. Suppose we have not two vector bundles, but several. Again, there is no real difference between real and complex bundles. So let's just consider both cases simultaneously. Now. So X is a smooth manifold. Which is assumed compact without boundary. An elliptic complex is a sequence of differential operators which I denote d1, etc., dm minus 1. These must satisfy the following, must have the following properties. First of all di must have the same order. Let's denote the order k. Second of all, the sequence is a chain complex, meaning or co-chain, meaning di composed with di minus 1 is 0 for all I from from 2 to m minus 1. And third of all, the sequence of the symbols is exact. Exact meaning pointwise exact. A symbol is a map from the pullback of the bundle to T upper star, to the pullback of the other bundle to T upper star of X, and so it makes sense to ask whether or not the sequence of the symbols is pointwise exact, and we require that it should be in order for this thing to be an elliptic complex. Well, let's have a look at some examples.
Is it exact with zeros from the left, at the left and the
yes, yes. Let's say that. Okay, let's. Okay, let's put zero vector bundles on the left and on the right, and then we get zeros on the level of symbols.
And one question: is it exact? Is it exact? Is a map of vector bundles or fiber-wise?
Well, it's the same thing, really. What is when is a sequence of maps of vector bundles exact? Well, the first definition that comes to mind is to require that it should be pointwise exact, and this is what this condition says.
I think it's stalk-wise exact, but it's not equivalent to be fiber-wise exact.
Well, stalks, so symbols are maps from the pullback, are maps of the pullbacks. Now, what does this thing say? It says that on the level of the stalks over x psi for each x psi, the sequence should be exact. It's the same. Let's remember that symbols are not maps of the vector bundles themselves. They're maps of the vector bundles pulled back to the cotangent bundle of X. And then we require that this sequence of the maps of the pulled back vector bundles should be stalkwise exact. Okay, well, maybe let's look at some examples, and then we'll get the hang of it. Well, the first example. Any elliptic operator gives us an elliptic complex. Just for for obvious reason, there's just one operator, so we don't need to worry about the orders being different. Now, this sequence is obviously a complex. And we all remember from linear algebra that a sequence two-term sequence is exact if and only if the map is an isomorphism. So basically, for sequences of vector bundles of length 2, we get back precisely the definition of an elliptic operator. Well, let's consider another example. Let's consider the de Rham complex. As we saw a couple of weeks ago, on the nose, none of the operators D1, etc., is elliptic. But let's see what happens. At least we know that all the components of the de Rham operator have order 1, so the orders are the same. Condition 1 holds. Condition 2 holds as well. We know that d squared is 0. Condition 3. Well, let's have a look. We know the symbol of the de Rham operator. Let's see. So two weeks ago, or 3 weeks ago, we calculated the symbol of the de Rham operator, and we saw that at a point x, psi, which is an element of the tangent bundle, the symbol multiplies everything by psi.
It's on the other side.
Okay, maybe. Okay, but this doesn't really matter. We know from linear algebra, and it's not very hard to prove that wedging by a non-zero element of this vector space is exact. Gives us an exact sequence of the exterior powers. It's called Koszul's lemma, or Koszul's theorem. It's very simple, but nevertheless it's important. So so suppose V is a finite dimensional vector space. And suppose psi is a non-zero element of V. Then we then we can form the following sequence. We take the 0th exterior power, which is just the ground field, let's say R, then the first, the second, and so on, and finally the last one, and the rest are 0. And then we take the maps from each space to the next, given by wedging with a fixed non-zero element of V, and the result is an exact sequence, which is not very hard to prove. Okay. Okay, so we have an example of an elliptic complex, and there are many more similar examples. For example, there is we saw the Dolbeau operator a couple of weeks ago, and these are not elliptic on the nose, but they give rise to elliptic complexes. The same applies to several other versions of the de Rham operator. We'll see a few examples later on.
May I ask a question?
Sure.
Should we add that xi is not zero?
Well, let's see. So. At 0, well, we already know that the symbol is okay. Let's see. The symbol is homogeneous of order k, where k is the order. So when psi is 0, all symbols are 0 as well. Okay, and yes, probably. Yes, when we have a sequence of yes, let's say let's say for psi different from 0, because for psi equals 0, the sequences consists of 0 maps, and it's not exact. Okay. Well, let's see. Okay. Are there any more questions? Now suppose all vector bundles all vector bundles have been equipped with a metric. Then, as we saw last time, it makes sense to consider the joint operators, and these will be again differential operators of the same order. So we have the operators di, and we have the joint operators which go in the opposite direction. And have the same order. Let's let's form an operator D by taking D plus D conjugate. I don't know the name for this operator, but we'll use it many times. I'll take it. It'll be quick. Алло. Нет, у меня сейчас занятие. Если что-то срочное, то значит тогда давай позже. Okay, well, we have D plus D conjugate. Which is self-adjoint.
Where does this attractor act?
Well, yes. So it acts from the direct sum of EIs to itself. Now, another operator is the square of this one. And as opposed to this one, the delta operator preserves every vector space C infinity EI. So this operator is called the Laplacian. of the elliptic complex. Okay, now now let's prove a few simple things about elliptic complexes. Well, the first one is that D and delta are elliptic operators, which is basically linear algebra. Plus the facts about the symbols, which we saw last time.
What do you mean when you say that D is elliptic? I don't understand. So I think we need to explain why is it differential.
Well, it's the sum of two differential operators of order k.
We
So
define the differential operator as a map from C-infinity sections of one vector bundle to another.
yes. So in this case, the vector bundle is just the sum, the direct sum of all the individual bundles.
Okay, thank you.
And then we basically we need to check that the order is the same as the order of each component. And we need to check that the symbol is an isomorphism. But we already know how to calculate the symbol of delta star if we know the symbol of delta. We know how to calculate the symbol of D star if we know the symbol of D. Basically, we have the following thing. We have a complex of vector spaces with a metric. Let me just state something about linear algebra, and then we'll see whether or not it's clear or true or false. But let's at least state it. So linear algebra. Euclidean vector spaces. V1, etc., Vm. And suppose AI are linear operators such that the sequence is exact. Then A plus A conjugate is an isomorphism. Each of the vector spaces is equipped with a metric, so it makes sense to finite dimensional. Each of the spaces has a metric, so it makes sense to talk about an adjoint operator. Well, my claim is that if this thing is exact, then the operator plus the adjoint operator viewed as an endomorphism of the direct sum is exact. Now, this time what we have is a statement about vector spaces, about finite dimensional vector spaces. So, well, A is the sum of AI, and this is the sum of AI conjugate, which where we view both this and this as an endomorphism of the direct sum. And by the way, it's the same notation I used here without explaining it. So D and D upper star is the direct is the sum of all di's. What does this mean? Well, I have lots of vector bundles, E1, etc., and I have maps from each vector bundle, from sections of each vector bundle to the next. Well, I consider each of these as an endomorphism of the direct sum, and then I take the sum. Okay. Well, once we've understood the notation, the statement becomes just some statement from linear algebra, and my claim is that the statement is true, and moreover, it's not very hard to prove. Let's leave it as an exercise. So this takes care of basically this takes care of the first operator. What about the Laplacian? Let's see. So we. And by the way, let's come back to this example. So here we have D, which interchanges all the vector bundles, but the Laplacian preserves every vector bundle. Why? Well, because first we go one step up, then one step down. And here we go one step down first, and then one step up. So the Laplacian operator is, in a way, simpler than the operator D, which mixes everything up. But we know that the Laplacian is d squared by definition.
I guess we can say when it's the partial algebra thing again.
And hold on. So the Laplacian is d squared by definition. And we know that if the square of something is invertible, then the something is itself invertible. So maybe to check this statement, it would be easier to handle the Laplacian first, because it preserves every vector bundle.
May I ask a question about the first part?
Sure.
About D. When the symbol of the conjugated operator is a dual operator to the symbol, but with sign.
Yes. So with signs, yes, it's a very good remark. Now, it may be that I have forgotten the signs somewhere. Let's see. So, if the order, in most examples, the order is 1. The order will be 1. So, if the order is 1, then the signs are correct. If the order is different from 1, then we might want to get an extra sign here in the Laplacian.
We know the formula that there is minus 1 to the power n, where n is an order. So when order is 1, the sign appears.
No, when the order is 1, the sign doesn't appear. But let's think a little. So we want this operator to be self-adjoint. So this operator is blah 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 blah. So this. Okay, so let's think a little. Maybe it's a false alarm. Maybe there aren't any sign problems. But let's think a little. Okay. Well, let's do the following. Let's erase this part and keep only the part about the Laplacian. What does this give us? Well, if we have to multiply something by -1, we get it both here and here, and this that doesn't change the fact that it's an isomorphism. So the idea is prove the statement for the Laplacian first, and then deduce the same statement for D. And we don't need to remember the signs. Okay, now the second property D and delta have the same kernel. Well, normally the kernel of the square is larger than the kernel of the operator itself, but the operator is self-adjoint, as is this one. Suppose we have an element of the direct sum such that the delta applied to S, is 0. And we want to show that delta, that D applied to S is 0. Well, what do we have? We have then ds is S d squared S S delta S is 0. And so ds is also 0. Here we use the fact that D is self-adjoint. So we can swap D from the left to the right and vice versa. Does this make sense? Okay. Now, what else? Okay, now Starting from D, we can form two operators. One from C infinity of the direct sum of the even bundles, and to C infinity of the direct sum of the odd bundles. And we call this operator D plus, and there is also D minus, which goes the other way around. Basically, the operator D interchanges even and odd, and the Laplacian preserves both. Okay, now the next thing we want to mention is that D minus is the conjugate of D plus, and and vice versa. Let's remember that we need to deal with the Bray-Hilbert spaces, not Hilbert spaces. So the conjugate may or may not exist, but if it does exist, if it does exist, then the conjugate of the conjugate is the operator itself, which is not the case in some other situations when we need to deal with operators which are not everywhere defined, but that's a separate story. Okay, so well, basically, well, it's a straightforward check based on the fact that D is self-adjoint. So suppose we have S. And we decompose it as S even plus S odd, and what do we have? We have D S even plus S odd. Let's see. Let's start with what we want to prove, and then we'll. So we want to prove that. D plus S even S odd is the same as S even D minus S odd. This is what we want to prove. How do we prove this? Well, well, let's remark that this thing is the same as d plus d minus applied to S even. Why? Well, because d minus annihilates everything, all even elements. And similarly, this is d plus d minus S odd. And then we just use the fact that D is self-adjoint. So the operators d plus and d minus are the adjoints of one another. Okay, so we've checked this. Are there any questions? Okay, now let's remember again that we work with pre-Hilbert spaces, not Hilbert spaces. So there are some surprises. And just to become aware of the sort of surprises one might encounter, the first thing one one of the problems that might occur, the adjoint operator needn't exist. And well, basically, it's not a very difficult exercise. In the Hilbert space, the adjoint of every continuous operator exists. So one could start with a case with the Hilbert case, and then take some dense subspaces of V1 and V2, and then basically choose an operator which such that there is something wrong with the inverse, with the joint operator on the level of the Bray-Hilbert spaces. Now, we will need to relate the index of a differential operator and the index of the adjoint operator. Now let's see what sort of things can happen, could happen, may happen, but may or may not. So suppose A continuous. There I want it to be continuous. No, I don't want it to be continuous. And suppose I have a linear operator, C linear or R linear, between Bray-Hilbert spaces, which I recall are just vector spaces equipped with the Euclidean or a Hermitian bilinear form, and this is it. The form is non-degenerate. Positive definite, hence non-degenerate, but we do not assume that the metric is complete. Okay, so suppose we have an operator such that there exists an adjoint operator. Now, we want to be able to say that the index of the adjoint if A is Fredholm, then the index of the adjoint operator is minus the index of the operator. This is what we want. But there is one technical condition, which is that this space must be complementable. We'll come to that. Now, first of all, does everyone understand what the orthogonal complement is? Now, this is the image, this is the kernel, and what I'm claiming is that the kernel of the adjoint operator is the orthogonal complement of the image of the operator. Now, do we want to prove this? So, well, it's not. We have 1 minute. Let's prove this, and then we'll decide what to do next. Okay, so let me take x inside the kernel of A star. I want to prove that X is orthogonal to the image. So, okay, let me take Y inside V1. I need to prove. I need to prove that AYX is 0. Well, this is precisely if I manage to prove this, then I will prove that X belongs to the orthogonal complement of the image of A. Okay, well, this is the same as Y A joint X, and this is indeed 0 because X is in the kernel. Okay. Well, let me prove the other inclusion. Suppose now I have X inside the orthogonal complement of the image of A, and I want to prove that X is in the kernel of A star. Well, I need to prove that A upper star of X is 0, which is the same as to say the scalar product with itself is 0. Okay, blah 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 blah. What does this give me? Well, this gives me so this scalar product is the same as A upper star X comma X. And this is indeed 0. Why? Well, because this part belongs to the image of A. And we know that X is orthogonal to the image of A. Okay. Now, we have proved these two vector spaces are equal. Now, and the question is, can one claim that this vector space is the co-kernel of A, which means the quotient of V2 by the image of A? And the answer is sometimes, but not always. And namely, this will be the case if the image of A is complementable. And we'll talk about this after the break. Now, if basically, okay, Okay. I may have asked this, but I've forgotten the answer. How many of you have already taken a course in functional analysis? 2, and you're taking one now. Okay, so well, I'll try not to spend too much time on obvious things, but on the other hand, we're not in a hurry. If there are things which need some explaining, we'll discuss those things. Are there any questions? Okay. Now let's see. I'll just get rid of. Okay, so what do? We pause the recording, we start a new one, what do? Новый слот, хорошо, тогда, well, let's turn it off and then restart it in about, well, let's have a break until